Our AERO 320 final project studies the dynamic system of Cephalopod Jet Propulsion.
The system being analyzed is the biological function in cephalopods used for instantaneous high-velocity travel, known as Cephalopod Jet Propulsion. For the detailed portion of this project, the focus will be on the squid species Logo vulgaris, pictured to the right. The system in consideration is the control volume containing the cephalopod and the surrounding water. Using means of muscle contraction to manipulate volume of the passages, a pressure difference is created to increase the velocity of the water jet, which propels the cephalopod forward. Mass and momentum are conserved in the process. The system is three-dimensional. The specific tested squid example is a squid with a mass of 350 grams with a siphon area of 1.5 centimeters squared and a fully contracted mantle cavity volume of 160 milliliters and a maximum mantle cavity pressure of 300 grams per centimeter squared. The anatomy of a squid and other similar cephalopods with similar bodily structures shows that they have a mantle cavity, which holds the water they use for jet propulsion and breathing. They have a siphon, which is the tube-like organ that shoots out the water, and they have gills located inside the siphon to collect oxygen from the air for cellular respiration. The eye is the organ that provides sensory information to the squid about its surroundings. Cephalopod jet propulsion is hundreds of thousands or potentially millions of years old. Marine biologists and paleontologists are actually unsure of which species of cephalopod was first to use jet propulsion. Paleontologists also know several precursor species of cephalopods which are not cephalopods but still had a siphon. As cephalopods and similar species do not fossilize well, these creatures are difficult to study and it's unclear whether the siphons on these creatures were used for jet propulsion or some other use.
Cephalopods use jet propulsion as an escape maneuver to keep away from predators. This, however, is an energy-intensive process. The jet propulsion efficiency decreases as the cephalopod ages and grows larger as the thrust increase is outpaced by the mass increase.
So for similar processes, we have the pump jet, the jet engine, the air circulation within animals, and pneumatic pumps. To analyze this problem, we're going to have two coordinate system frames. The first one is an initial reference frame, which is relative to the Earth and its rotation, and the second reference frame being the one attached to the initial position of the squid, oriented so that one axis lies along the direction of motion of the squid.
In a biological system, or any biological system for that part, the main form of gathering data is through specific sensory organs and sending the information to the nervous system. This system therefore has the primary input as the squid's sensory inputs. After the initial control law condition is set, the other inputs to calculate the output include the mass, velocity, and acceleration of the squid, along with the pressure of the cavity, frontal area of the squid, and density of the water. In our system, the primary output of the system is the squid's new motion relative to the squid. Additionally, other terms that are used as outputs include new velocity, new cavity volume, and new mass. Note the new mass can be calculated using the additional conditions and the new cavity volume. The quantities measured in the reference experiment measure the quantities of the velocity of the squid, the drag created by the motion of the squid, the pressure in the mantle cavity and the surrounding environment, the thrust produced by the jet propulsion, the distance the squid moves over time, the time the process takes, and the weight of the squid. Using equations for mass flow rate and jet velocity, we can derive the equation for thrust, which is modeled as a jet velocity multiplied by the mass flow rate. We can set that equal to the equation for thrust and can be modeled as a linear function of cavity pressure. Taking the equation for thrust into account, we can add this term to the general motion equation. In the end, the terms add up to the other terms of the general equation of motion. The first term contains the gravity forces. This term has the downward force of gravity and the upward buoyancy force. In the case that height does not change, this term cancels out as the upward force is equal to the downwards force. The second term is a drag force term. This accounts for the resistance as the water on the squid. The third term is the equation for Newton's second law. The result of this term is the force of the squid on the system as a result of the squid's mass and acceleration of the squid. The last term is the thrust equation that was derived previously, relating the thrust as a function of pressure.
The propulsion system as a whole fires in discrete intervals, as it can only hold so much water in the mantle cavity at a time and must take time to refill, so it ends up firing off in discrete intervals. The biological nervous system of the squid is also discrete-based, as it runs on discretely fired neuron responses. The firing of the jet siphon, however, is a continuous process that happens over the curve as the muscle around the mantle cavity contracts.
In reality, the squid is constantly taking in new sensory information to determine if it needs to continue moving or adjust its thrust. In theory, this can be treated as a negative feedback loop, where an output of using the jet, the new location, is directly fed back into the control law to determine if the squid needs to continue firing its water jet to reach its desired location. A cephalopod controls the motion created by its water jet by varying the intensity with which it contracts its mantle cavity. The cephalopod control law approximates how a cephalopod will use sensory inputs to decide that it needs to move a certain distance, and then apply corresponding pressure to create a water jet and propel itself. Through the negative feedback loop, this will continue until it reaches its desired location. The block diagram of the system shows the interactions between the different components of the system. Yellow lines show data transmission between components, blue lines show fluid flow between components, and red lines show force acting between components. The input of the system is information from the surrounding ocean being perceived by the squid's sensory organs, and the output of the system is force from the water jet acting against the squid to create motion.
The performance metrics are the thrust and velocity produced by the cephalopod. To escape from predators, it is important that the cephalopod can attain a high velocity in the shortest amount of time possible, while maintaining a safe distance away from danger. The cephalopod can reach its top speed of 2 meters per second in as low as less than 0.2 seconds, which provides a good burst to run away from danger. According to the plot, the cephalopod can move about 0.65 meters in 0.8 seconds, which is pretty advantageous considering they are typical predators. This plot visualizes how the major forces vary with respect to time in our system. Right when the jet stream is produced by the cephalopod, the thrust force is at its maximum and decreases pretty quickly over time. The drag is proportional to the velocity of the cephalopod, and which reaches its maximum value when the cephalopod is at its maximum speed just below 0.2 seconds. After the thrust goes down to zero, the drag keeps slowing the system down until the system attains a zero velocity unless another jet stream is produced by the cephalopod.